Lecture 3 of current week. Course code is CS430. Course title is Microprocessor. In the previous lecture, we have covered following topics. First of all, we covered real mode memory addressing. We discussed that how uh, physical address is calculated. Then we discussed the real mode memory and how segments are located in real memory, and the concept of relocation of segments and the concept of paragraph is discussed. Then we discussed protected mode memory addressing, and we discussed the structure of a segment register, how the selector, table indicator and RPL is present there. Then we discussed the how selector is accessing uh, descriptor, and descriptor tables are discussed. And then in the last we discussed access byte. Now we have to start this lecture. In today's lecture we have to discuss the concept of program invisible registers present within 80286 processor and onward. We will be discussing what are the registers present in this portion and for which purpose these invisible registers will be used in accessing memory during protected mode operation of processor. Then we have to discuss how a processor may switch from real mode operation to protected mode operation. Then an example of protected mode memory addressing will be discussed. How 80386 and onward processors may access some descriptor, and from that descriptor base limit access write byte will be fetched, and then we have to locate initial and final address of a segment in that example. So that will be the end of protected mode. Then we have to start a new topic of addressing mode. So we will be listing all the addressing modes present within 8088-8086 microprocessors. Then we have to start discussing their types. So some basic types of addressing modes will be discussed in this lecture. In all the processors starting from 80286 till Pentium 4 who support the protected mode memory addressing, they all have program invisible registers, and these registers are not directly accessed by software, so they are called program invisible registers. So these registers will be storing the starting address of global descriptor table as well as local descriptor table, interrupt descriptor table, and there is also another register, task register, and all the segment registers present in the 80286 processor and onward. There is a portion for storing the base address, limit, and access side byte, which is accessed from the corresponding descriptors. As we know that we store a number in segment register, and from that segment register a selector is extracted. That selector selects a descriptor in descriptor table. From the descriptor we get segment address, starting address, base address of the segment, and limit and access side byte. So all these informations are stored in the cache portion, which is called program invisible register. Until the number present in segment register is valid, the base, limit and exercise byte are valid. So there is no need to access descriptor again and again, but whenever you are executing some instruction and accessing data segment or stack segment or code segment, there is no need to load again and again the values for base, limit and exercise from descriptor. But this program invisible register portion will be used for getting the base address of the segment, and offset addresses generated by the program will be added with the base address to calculate the physical address in memory where you are having data or code. So this portion of memory registers, program invisible registers, are called cache memory when you are accessing memory in protected mode memory addressing. This diagram you may see that program invisible register portion is shown. 80286 and onward processors are having this portion. Uh, in the bottom, you are having GDTR, global descriptor table register. Base address of global descriptor table and limit will be stored there. And interrupt descriptor table base address is present and limit will be stored there. And LDTR will be loaded with a number of 8 bit, 16 bit, and that will be depending upon the uh, application, current application which is to be executed, and base address, limit and exercise byte will be fetched from memory from descriptor table. Then you are having task register. So same is the case with for task register. Task register will be having 16-bit number, and base, limit or exercise byte will be loaded from memory from the global descriptor table. With the segment registers, there are 6 segment registers. We have to discuss the global descriptor table register, interrupt descriptor table register, local descriptor table register, and task register. So there are instructions for loading global descriptor table register with the base address and limit of global descriptor table, and that instruction is LGDT, global descriptor table instruction. So after loading the base and limit of global descriptor table, you will be loading interrupt descriptor table register with base and limit by using LIDT instruction. Then to load local descriptor table register with base, limit and exercise, LLDT instruction will be used, and LLDT instruction will be accessing a descriptor of global descriptor table, and from there for the current application base address, limit and exercise of the local descriptor table will be stored. Then last register is task register. At the time of system initialization, a task is loaded within TR, task register, by using LTR instruction. After initialization, uh, task switching is performed by using call instructions. Now we are going to discuss the steps involved in switching from real mode operation to protected mode operation for 80386 and onward processors. The first step is to load base address and limit for interrupt descriptor table. For that, we are having an instruction LIDT that will be loading base address and limit for IDTR. At the time of initialization, interrupt descriptor table must be having at least first 32 interrupt gates defined. In total, IDT interrupt descriptor table may have 256 interrupt gates. Each interrupt gate is of 8 bytes. First 32 out of 256 interrupt gates are reserved for Intel operations, and remaining 224 out of 256 interrupt gates are user defined. So at the time of initialization of IDT, first 32 interrupt gates must be defined. Second step is to initialize base address and limit for global descriptor table. So for that we are having LGDT instruction. By using LGDT, base address and limit for global descriptor table will be initialized, will be loaded, and at the time of initialization, global descriptor table should be having a null descriptor at descriptor 0, and there must be valid descriptors for at least one code segment, one stack segment, and one data segment at the time of initialization in global descriptor table. Then we have to switch to protected mode operation. For that, in processor we are having uh, a, a control register CR0. The LSB of CR0 is having PE bit. PE bit should be having logic 1 to enter protected mode operation. So by using some instruction, we have to assign PE bit logic 1 within control register 0. Just after that, we have to perform an intersegment jump for loading a new stream of instructions, and as we are going to load a new stream of instructions, so internal instruction queue will also be reinitialized from the new location. After that, all the data selectors will be loaded in segment registers: code segment, stack segment, data segment, extra segment, and FS and GS. So new selector values will be loaded, and new descriptors will be accessed from memory, and values for base, limit, and access right for the segments will be loaded from descriptors. And now your processor is operating in protected mode, and uh, processor will be accessing global descriptor table and local descriptor table for loading different segment definitions. In this diagram, you may see the position of P bit within CR0. So CR0 is a control register within 80386 and onward processors, and P bit is the LSB of that register. This P bit is to be set for entering the protected mode operation, and for exiting from protected mode operation to real mode operation, P bit is to be cleared. So that is the purpose for P bit within CR0 register. Now we are going to discuss an example for protected mode memory addressing. In this example, given values are for data segment. Data segment is having 0013 hex, and global descriptor table base value is 9E087E50 hex, and local descriptor table base address is 3D4C6930 hex. And our task is to extract values from base, limit and access from the given descriptor portion, and also we have to find values for GD and AV bits. So from the given data, first of all we have to write data segment register in binary. So we have written here data segment register in binary. So that is the binary pattern for data segment 0000 0000 0001 0011. As we have discussed earlier that data segment register will be having 13 bit for selector. So the value for selector will be this one. That is the value extracted from this binary pattern of data segment. So that is the selector. So in hexadecimal that will be 0002 hex. Table indicator is 0 from the given data segment register, that is TI bit is 0. That means we are going to access global descriptor table. And last two bits are for RPL, requested provisional label. So RPL is 11 for the given example. Now we have to locate descriptor within the given chunk of descriptor table. As we have decided up till now that we are going to access global descriptor table. So GDTR will be having we will be having GDTR here, and for locating the select descriptor we have to use selector value. As we have discussed earlier that each descriptor is of 8 bytes, so we have to multiply selector value with 8 to locate the descriptor within descriptor table. So we have multiplied selector value with 8 hex, or in binary that will be 1000 B. So that is the binary value for selector. We have multiplied this value with 1000 B. So we will be getting in hexadecimal 10x. That 10x is added with the base value for global descriptor table. So we are having 9E087E60 hex. So that is the location, starting location of selector in memory, descriptor in memory. And as we know that descriptor is of 8 bytes, so that is the final address of descriptor. So our descriptor starts from 9E087E60 and ends at 9E087E67. As we have located our descriptor is starting from 9E, this address to this address. That is the boundary for our descriptor. In this slide, we are having a standard pattern for 32-bit processor for descriptor of 32-bit processor. So now we have to match values. This 3D is for limit. This 68 is for limit. And that is lower nibble of the second last byte is for limit 5. So total limit value is 53D68 hex. Now we have to locate uh, base value. So this 80 is base, 39 is base, 4F is base, and this 08 is base. So total value for base is this one, 08 4F 3980 hex. Now we have to locate value for access write byte. So that is the value for access write byte 92. That is 92 is for access byte. Now again we have to locate GD and AV bits. So that higher nibble of second last byte D is for GD 0 AV. If we write D in binary, that is the pattern. So G bit is 1, D bit is 1 and AV bit is also 1. Now we have to work for starting address of data segment within memory. That will be equivalent to the base address we have just extracted from descriptor. So that is the starting address of data segment within memory. For the final address of data segment within memory, base will be added with the value of limit. As we are getting G equal to 1, so limit will be padded with FFFH on the rightmost side. So limit value will be that one, 53D68FFF hex. That will be added with the base value, and that will be the ending address or final address of data segment in memory. Now we have located a data segment within memory. For that data segment, we have to calculate the actual addresses for protected mode memory operations. So here we are having two instructions, and we have been given contents for three registers: EX, EBX and ECX. And data segment base address is coming from the previous slide, and data segment final address is coming from the previous slide. So we have calculated address by using the given data. So first of all, first instruction is move EX comma within square bracket EBX plus 3040. That is the first instruction. So for calculating address, we have to add offset, that is EBX plus 3040 with DS base address for DS. So that is the final address you will be getting, and that is the physical address that will be appearing on address bus to access data from memory, and that data will be stored in EX. In second instruction, you are having move within a square bracket EX plus ECX comma EDI. So register of 32-bit is copied onto memory. So offset address here is EX plus ECX, and base will be coming from data segment base address. So the final calculation is result is 4C9082B0 A82B2. So that is the calculation for protected mode memory addressing. So up till now we have completed discussing protected mode memory addressing for x86 series processors. Now we are going to start a new topic that is called addressing modes. Addressing mode means the different techniques of mentioning operands for an instruction are called addressing modes. So there are different instructions. Some instructions deal with data, some instructions deal with program branching, some instructions deal with stack operations. So we have divided addressing modes in three categories. First one is data addressing modes, for which we will be uh, considering move instruction for discussion of data addressing modes. Second category is program memory addressing mode, For discussing program memory addressing modes, we will be considering jump instruction. And third one is stack memory addressing modes, for which there are two instructions available: push operation instruction and pop operation instruction. So we will be discussing push and pop instructions in the stack memory addressing modes. Now we have to discuss data addressing modes. For discussion of data addressing modes, we have to consider move instruction. General format for move instruction is move operand 1 comma operand 2. So there will be two operands within move instruction, and data will be transferred from operand 2 into operand 1. So here in this slide you are having a list of addressing modes, data addressing modes. First one is register addressing. In register addressing, both of the operands will be processor registers. So data will be transferred from one processor register to another processor register. So there will be no involvement of memory in this mode. In second addressing mode, immediate addressing, first operand may be a register or memory address, and second operand will be an immediate number. So we will be discussing this addressing in later slides. Third addressing is direct data addressing. In this addressing mode, data will be transferred between processor register and memory. Memory address for this type of addressing will be mentioned by using a memory label or an direct address. That means no processor register will be used to point memory. There are subtypes for direct data addressing. First one is direct addressing, second one is displacement addressing. So we have to discuss these addressings in coming slides. Now after that you are having register and direct addressing. So details will be coming in the coming slides for register and direct addressing. Then there is register relative addressing. Then we have to discuss base plus index addressing. Then there is last 16-bit addressing mode is base relative plus index addressing. Scaled index addressing is for 32-bit processor. So we will be discussing this addressing briefly in coming slides. Now we move to first data addressing mode, that is register addressing. For register addressing, general format for move instruction is move register 1 comma register 2. So both operands are registers, processor registers. What is not allowed in this addressing is mixed sizes. So if your register 1 is of 16-bit, register 2 will also be of 16-bit. If register 1 is of 8-bit, register 2 will also be of 8-bit. No mixed size is allowed, and there is a limitation that segment register may not be copied directly into a segment register. Third condition is that code segment register may not be mentioned as register 1, because we don't want to change the value for code segment, because if we change our code segment value, we will not be able to access our code. So that is not allowed to write CS register as register 1 in move instruction. Then what is allowed? Index register may be copied into index register. Pointer register may be copied into pointer register. It is allowed. Some examples are given. Right. So that is some examples for move instructions. First one is move ax comma bx. Ax is of 16 bit, bx is of 16 bit, bx will be copied into ax, bx will remain same, ax will change. In second instruction, move bh comma dl. Bh is of 8 bit, dl is of 8 bit, so dl will be copied into bh. Contents of dl will remain same, bh contents will change. Third instruction is move bp comma sp. So you are having pointer registers here. bp is base pointer, sp is stack pointer. Both registers are general purpose registers of 16 bit. So contents of sp will be copied into bp, sp will remain same, bp will change. Then you are having another instruction move di comma si. So here we have used index registers. So di destination index, si source index, both are of 16 bit. Si contents will be copied into di, si will remain same, di will change. Then we are having another instruction move ds comma dx. So here we are having a segment register ds data segment, and second register is dx data register, simple register, general purpose register. So that general purpose register dx will be copied into ds, and a special purpose register it is allowed. Both are of 16 bit. dx is of 16 bit, ds is also of 16 bit. Next instruction is move ax comma es. Here you are having an special purpose register extra segment. Content of that special purpose register is copied into a general purpose register ax, so that is allowed. Size of both registers are same. es is of 16 bit, ax is also of 16 bit. So if you want to copy a segment register into another segment register, you may copy segment register contents into a general purpose register, and that general purpose register may be copied into the second segment register. Now we are having some examples for not allowed cases. First one is move ah comma bx. Here ah is of 8 bit, bx is of 16 bit. So mix sizes are not. After register addressing, second type is immediate addressing. In immediate addressing instructions, first operand may be processor register or memory address, and second operand will be an immediate data. So if the first operand is memory, then a pointer should be mentioned with memory address to declare the size of the data mentioned after comma or as second operand. So that is compulsory to mention a pointer with memory address if you are having immediate type of instruction. So here we are having some examples for immediate addressing instructions. So first example is move ax comma 9f hex. Here processor register ax is involved and immediate data 9f hex is present. So this 9f hex will be converted into word by placing two zeros. So 009f hex will be moving into AX register of processor. In second instruction, an 8-bit register is present CL, and immediate data is 10101 binary. So data type for immediate data is binary. Equivalent hex of this binary number is 15 hex. That will be moved into serial register of processor. In third instruction, we are having move di comma 13650. So data type here is octal. So this octal number will be converted into hex. Equivalent hex is 0 to 5 F5 hex. So that hex number will be moving into destination index register of processor. In fourth instruction, SP register of processor is involved, and 16-bit number is mentioned on the after comma as second operand D468H. So as we know that for hexadecimal numbers we are having alphabets as digit. So wherever there is a case when hexadecimal number is having an alphabet on the leftmost side, so for declaring for processor that is a number, not a processor register name, we have to place a 0 on the leftmost side of that number. So we have written 0 with D468H for declaring this as a number. So SP will be having D468H after execution of this instruction. 0 is only declaring this as a number, and that that is the purpose of 0. Now after that we are having two instructions for memory immediate type of instructions. First instruction is move byte pointer within square bracket bx plus 30 hex comma 4eh. So as we have mentioned earlier that with memory immediate type of instruction pointer is a must. So that byte pointer is declaring 4e as a byte. So 4e will be stored within data segment at offset bx plus 30 hex after execution of this instruction. Last instruction here is move word pointer within square bracket si plus 1050 hex comma 10,000. With 10,000 there is no suffix is placed. That means that number by default will be treated as decimal number. Equivalent hex number of this decimal number will be moving into memory as word, because we have mentioned with memory address word pointer. So 2710 hex, that is the equivalent of 10,000 decimal, will be moving into data segment at offset si plus 1050 hex. So 10 will be stored at si plus 1050 hex, and 27 will be stored at si plus 1051 hex within data segment. So that is the end of the today's lecture.